This section of notes is on electric current and electric circuits. Had we had a normal year, this would have been something that would have been a required assignment, building your own flashlight out of all recycled household items with the exception of a battery and a light bulb. And so if you have something you want to try just for fun, go ahead, but that is not something that is going to be required. So what we're doing is we're going to be looking at how to complete a circuit. We just got done talking about capacitors and potential and voltage. So I know in previous classes you've done this. How is it that you would light up a bulb? You got to have a power source. That power source most likely is going to be a battery. It could be the holes in the wall. It could be a capacitor that's charged up. You have to have conductors. You can't make your light bulb light up by using a battery connected with a bunch of string. It's got to be metal. So that's why we have metal wires in the form of copper wires. We have to complete the circuit. We have to give the charges a path from, going up here, high potential to low potential. So we have to give the charges a path to go from the positive end to the negative end of whatever you're using. It might be the battery, and the battery is very clearly marked for you, positive end, negative end. It might be a capacitor that you have charged up with a positive side and a negative side. Remember, we are talking as if positives are the charges that move, because that's how our rules are defined, even though we have since found that the negatives do all the moving. We are going to speak as if the positives move. So we got to have our positive and negative connection to our potential difference, and we have to have actual contact. You don't have to glue them together, weld them together, tape them together. You can simply touch them together by using your hands and pressing the metal together, and that is enough to make all the metal act like one. And now you have a continuous path from the positive end to the negative end, and the charges will naturally flow from high potential to low potential. No different than particles naturally falling down with gravity. High potential up high, it naturally falls down to low potential down low, as long as there is a path. So if I have a table in the way, my tennis ball can't go to lower potential. But as soon as I put a ramp, now it can flow. That's what the wires are. It's a path to lower potential, just like a ramp for my tennis ball. So these are some notes that we can fill in the blank. Charges only function for us when we get them to move. Sometimes they move in a sudden burst called an electric shock. We want constant controlled charge motion. Now when we do this, the moving charges, everything has positive charges in it. So what happens is we just get them all moving. And this is where we would usually do a demonstration in class with a bunch of students. I'd bring up 5 students and I'd say, okay, you are waiting in the lunchroom line, you are waiting in the Cedar Point line, move forward. And what happens? The first person moves forward, then the second person moves forward, etc. The first person stops moving, and then the second person catches up and stops, etc. That's not how charges work. Charges instead, and we would do this in class, charges work like a marching band. Every single person steps forward with their right foot, and they can do that without fear of stepping on the person in front of them, because they know that the person in front of them is going to step forward with their right foot. And so everybody marches in unison. They start together, stop together, everything moves at the same time. And that's exactly how charges move. As soon as there is a potential difference of voltage, everything starts to move. What is needed for a circuit to work? We already mentioned this. We need a path that is made up of conductors, and it needs to be complete. We call it a closed loop. And we have to have a power supply, our potential difference, which for us is usually going to be a battery. So our voltage is, again, measured in volts, joules per coulomb. This is what gives the charges energy. Charges can't move unless they have energy. The energy comes from the voltage. Current is capital I. Current is the flow rate, how many charges go by in a given amount of time. So coulombs per second. We call that an amp, capital A. The variable is I, the unit is A. We have resistance. Resistance is opposition to current. So when the charges try to flow through our conductors, there is a little bit of resistance. It's not friction, but we can think of it like friction. So as something is moving, friction is there slowing us down. It's not friction between charges, but it behaves the exact same. This right here is pronounced ohm. This is the Greek letter omega. It kind of looks like an upside down horseshoe of sorts. Volts per amp. We'll talk about this equation in just a second. The resistance, what does our resistance depend on for our devices? We'll talk about that here in just a second. Battery symbol, we talked about that already. Resistor is just this little zigzag of a wire. Sometimes we'll put a circle around it if it's a light bulb, but that is not necessary. Now when we talk about the total resistance, so if I've got 3 light bulbs that I'm all lighting up, then I have a total amount of resistance. Instead of calling it total, in physics we call it the equivalent resistance, REQ. So we'll talk about that from time to time. Now, series. A series is when you have a single path. So you have a battery and then you go from one resistor to the next resistor to the next resistor. What happens? My current has to be the same. I can't create or destroy current. So if I have one single path and I have 5 charges go by every second, every single device must have 5 charges going by every second. If I get 6 charges going by in a second, where did this extra charge come from? If I only have 2, where the other 3 go? So I'm getting this constant current. Voltage is shared. If my battery gives me 12 volts, everything uses up a little bit of the 12, so they share it. They don't share it equally, but they share. And the resistance is simple. Resistance is add them up. If my first light bulb has a resistance of 2, and my next light bulb has a resistance of 3, 2 plus 3 is 5. So it's very, very simple. Now when it comes to parallel, we're not going to worry about the overall resistance, but once I have a picture, it's going to kind of help you here. But the current's going to be shared. Multiple paths is how we define a parallel circuit. So basically I get a break in the wire. I can go left or I can go right, which means that my charges, when they get to that point, my current has to split up. I can't have all the current go down one path when I have a second path. So it splits up. And what happens is every time I add another path, it makes it easier and easier for the charges to flow. Don't worry about this equation right here. Don't worry about the derivation up here. Don't worry about that. Just know that the more resistors you add, the easier it is for charge to flow, and my battery has to push out more and more and more current. If I come down here, my example is lanes of traffic. Every time you open up a new lane, when you're driving your car, if you go from 1 lane to 2, traffic flows easier because you now have 2 paths. If it's 3 lanes, 4 lanes, 5 lanes, every lane you add makes it easier. What if you open up a really, really, really bad lane with potholes and broken glass? Well, I'm sure one car will go that way if there's no one in its way, and even one single car taking that path makes all the other cars move just a little bit faster and smoother in the other good lane. So it doesn't even matter how big the resistors are. So that's for our parallel system. Multiple paths. Every path has the same drop in voltage. So if I'm going to do a river analogy here, it's going to really help, I think, but when my current splits up, each path has to fall the same amount before it reconnects. So when it comes to resistance, this right here is a wire coming in, and this is the wire for my light bulb. You'll notice I drew this one really, really skinny and narrow. Well, when it's really, really skinny and narrow, it's hard for the charges to go through because the wire is so thin. If I scroll down a little bit, what happens if I make the wire a little bit thicker? I can fit more charge through and my current goes up. What happens if I don't put anything in there? What if I just have a wire? Well, everything just flows with a consistent speed. And that's going to be important when we start talking about our resistance. So here is our resistance. It's opposition to charge flow. Charge flow is current. It's not friction, but it acts like it, and depends on how you build your wire. I look at a lot of our electric current, I look at it like water current. So if I had a straw, what would make the resistance easier or harder to go through? One of them is going to be the thickness. Think about a normal straw from McDonald's sipping soda through the straw. Now, what happens if you take one of those really, really skinny, narrow straws that are designed to stir coffee? I know we've all done it. You use that tiny little straw, you don't get much fluid because the resistance is huge because there's not a lot of space for the fluid. So when the area goes down, skinny little straw, the resistance goes up. If you get a really, really thick straw, you go through that soda, you go through that fluid very, very quickly and easily. That's why if you're drinking something like a milkshake, you need a really wide straw because it's hard to draw that fluid through. Okay, the next one down here, L, length. The longer the straw is, the harder it is to get your fluid to flow through. I don't use those really fancy, cute, bendy straws, but I do know that when I have used them, it's really difficult to drink your fluid through that, at least when you compare it side by side with a straw that's not so long. Because that twisty, bendy, curly straw, imagine straightening that straw out. You have a straw that's like almost 2 feet long. You curl it all up and makes crazy little shapes. It's much more challenging to draw fluid through that. And the last thing is this Greek letter, the resistivity. That depends on the metal. Some metals are better at transporting charge than others. And so we put this into this equation. So how resistive is the metal? How long is it? The higher those values are, the more resistance you get. And then you divide that by the area. So that means if my area is bigger and bigger and bigger, my resistance actually gets smaller. It's easier to move through. So when you look at the filament of a light bulb, it's really, really skinny, so small area, and it's a twisty, curly wire, big length, which means your light bulb actually has a really big resistance, which is why it glows. It glows with heat. The old school incandescent light bulb with the wire glows because it gets so hot that it actually glows. The newer, more efficient light bulbs don't do that. They use different methods. Right? So that right there is what your incandescent bulb would look like if you looked at it really close. The wire is so skinny it's really hard to see, so you got to really pay attention to it. This leads us to Ohm's law, very easy equation. What happens if I have twice the current? That means my particles have twice the energy. What happens if I double the energy? I'm going to have twice the current. If this line goes up, so if I take this line here and I increase it, what does this mean? This means that to get the same amount of current, I need way more voltage. I got to push harder to get the same current. If I do this, what does it mean? It means that I get a lot of current with just a little teeny tiny push. That is our definition of resistance. I can get a lot of current with not a lot of push when my resistance is really low, and vice versa when I have resistance that is really high. So we have this equation here, V equals I times R. So that means our ohm is a volt per amp. Now there are devices that vary with current. If I scroll down just a little bit, a light bulb, the hotter and hotter and hotter it gets, the worse it becomes in terms of its resistance. You actually get a curve. So anytime you have a curve or a non-ohmic device, it means temperature matters. And we're going to keep it simple. We're going to say, you know what? We're going to ditch temperature and just go with this equation right here. Ohm's law, V equals I times R. If you know the Spanish language, this is the verb to go, and all the conjugated verbs, I think, start with the letter V. I think that's the right word, conjugate, but I don't know. But anyways, if you're a Spanish speaker, this usually has a little bit of a ring to it. Now, I've got this picture here. This is how your circuit works. One of these, I have one of these literally in class. Thank you to Christian Ryder and Dylan Blackmer from last year. They bought me one of these little toys. If you don't recognize this toy, you can go on YouTube and search penguin toy. And what happens, these little penguins get lifted up by the battery. The battery works this little staircase, and the penguins go up and up and up and up and up. And what happens? They slide on down, and they get back here, and they keep on going nonstop. It's exactly what happens with a circuit with current. The battery takes the charge, pushes it to high potential. These little penguins wouldn't naturally go to the high location. That's what our battery is for. But then once they're at that high potential, how do they get back down to low potential? They can't go back down the stairs. It doesn't work that way. They got to take the long way around. They got to take all the way down and then back. Same thing here. Can't use this one because we got ups and downs and twists and turns, so that's why we can't use this. But for water slide, you start high and you just go down, 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 down. Sometimes look at the blue slide. Sometimes you have a quick drop and then a flat drop. Sometimes you got a straight drop. Sometimes you got twists and turns, but no matter what, you're working your way down, 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 down. You get to the pool. You're at the ground. How do you ride again? Stairs. Stairs are the battery. You walk up the stairs, you get to the top, and then you go down. That's the wires and the light bulbs. And then you go through the battery back up, and then you go through the orange wire all the way down, and you light up a bulb. And then the charge goes back up the stairs. Repeat, repeat, repeat. So if I look at this, this is what my graph would look like if I had voltage. Let's try that again here. If I had voltage and I had the different devices of my system, I got here and here and here and here and here and here. If I look at it that way, what do I have? I have a battery giving my particles that have no energy. We gain energy, and then I have a wire that uses some energy. I have a light bulb that uses a lot of energy because I get light and heat, and then maybe I get another wire, and then maybe another bulb, and then another wire. That's what my graph would look like. If I did this, there's my battery right there. There's my light bulbs. Right? What I'm looking at is a big positive change in voltage, and then a little bit of a drop, and a drop, and a drop, and a drop. And you can see a water slide here. That's exactly how our current works. What happens when a charge gets to the bottom? The bottom is the negative end. It gets pushed back up to the top, and this thing here just happens again and again and again. Energy from the battery and then used up, and then energy from the battery and then used up. So that's why we talk about voltage drops quite often when we look at circuits and currents and things like that. We call this the loop rule. Do I have it written down here? I do not. We call this the loop rule. The loop rule says, let's see if I can write it out here. The loop rule says, why is this not working? Let's try this one more time. There we go. The loop rule. The loop rule says that as you go around the circuit, you use up every bit of voltage. You gain voltage and then you use it all up. Think about the water slide. You can't go halfway up. You got to go all the way to the top. You can't just go halfway down. You got to go all the way to the bottom. You got to go through the whole thing. So you go up 50 feet, you got to go down 50 feet. You can't go up 50 feet and just go down 10. You can't go down 50 feet and just go up 13. You have to go all the way up, got to go all the way down. We call that the loop rule. Right? So we have worksheet 3, which is posted, and I have solutions there that you can look at. This right here, I've got 3 bulbs, and I've got a battery pack. And then I have 2 battery packs and 3 bulbs. So if I skip forward, there's 1 battery pack and 3 bulbs. Our wires here and here and here, our wires use up such a small amount of voltage that we practically call it zero. It's kind of like, when we used to say, oh, air resistance doesn't really matter. Same type of thing. So I have 4.5 volts given to me by my battery, and then I use up through my 3 light bulbs. What happens if I use 2 batteries? Well, it's like having 2 sets of stairs. I go up the first set of batteries, and up the second set of batteries, and then I have to use it all up. Here I have 4.5. Each one gets 1.5, 1.5, 1.5 until my charge gets back to 0. Here I got 9 volts, which means I get 3, 3, and 3. So I get brighter bulbs because I have more voltage. So that helps us with the worksheet. Part C, if you look, the batteries aren't side by side. I'm sorry, they're not one after the other. In B, I have 1 battery followed by the next, 1 set of stairs, then followed by another set. What do I have here? I've got 2 stairs side by side. Why would I have 2 stairs side by side? I can get more people flowing through, but I don't get any higher. So if this is my water slide, I can get more people through, but I don't get them any higher than having 1 single stair. So for that one, that's C at the bottom. We still get 4.5 as our height, so to speak, and we still get just 1.5 volts. Okay, some more samples there that you can look at. All right, so continuing now, don't need any of that. This right here is my water analogy. This is a river with a little green island in the middle of the river. If I have 1,000 gallons going by every second, and I have only one river, I have to have 1,000 everywhere. When the river's wide, the water can move slow. When it's narrow, my water has to move fast. This right here would represent my light bulb. The fast moving water means this V is velocity. Faster moving water means that I'm going to have a light bulb light up. When it moves slow through my wire, it doesn't light up, but I still have the same current going through. So if you remember a series circuit told us that we had the same current everywhere. Now what happens over here? I have a particular high voltage, and then my current splits up. I got current going down I, and I've got current going down 2. So as my current splits up, I'm going to have, if I have 300 here, I got to have 700 here. Those two add up to give me 1,000. We call that the junction rule. I have to account for all of my charges. Yes, I'm talking water here, but if I'm talking charges, if I got 1,000 charges here, 300 and 700, I add them up and I get 1,000. What happens when I get to the end? I get 1,000 again. Each individual branch, 300, 300, 300, 300, all the way down. For branch number 2, 700, 700, 700, until they reconnect. So what I have here, and you can look at the notes that I have posted, is a lot of information kind of reminding us about that. What happens when I have one branch, what happens when I have multiple branches. Now, if I look at branch 1 and branch 2, each branch has to fall the same distance. That's how a river flows, gravity pulling water downhill. I have to have the same drop. What happens if this side of the river dropped 50 feet and this side of the river dropped 100 feet? Well, what happens when they come together? The 50-foot drop has to fall down until they can match up. So if I look, this is a side-by-side. Path number 1, path number 2. Path number 1 might look like this, waterfall. Path number 2 might be a little more gradual. Doesn't matter what they do, they both start and stop at the same height. So what we find for our parallel is that we get the same drop in voltage for each branch. So, loop rule. The voltage through every single loop has to be 0. Whatever we get from the battery, we got to use up. Junction rule. Current going into a spot has to be equal to the current going out of the spot. And when I think about water and rivers, it works really, really, really well. All right, so we've got series, we've got parallel, and this is just a reminder. Constant current through a series, same flow rate, and they have to share. Every device gets a little bit of the total amount of energy. Here, parallel, I get the same drop, path number 1, path number 2, same drop. They share the current. So if I had 300 in the top branch, I had to have 700 in the next branch from our previous picture. This right here is something we would have done in class where I would have had you as a group come up and select from all of these. They all would have been piled up here in the middle, and you would have kind of come up and dragged them side to side and placed them in under the right category. We're not doing that, obviously, so that's just a slide for you to look at. So here, parallel. I have 2 parallel branches here. I don't have to have wires that are actually drawn parallel. Usually the way it is you have a wire connecting to one side of your light bulb, and then you send a wire from there to the next light bulb. If you were actually wiring a house, you'd have the power supply of your house, and you would have one big wad of wires all kind of connected together. They'd go to your light bulb, and then you would cut them open, and you'd connect to one side of the light bulb and the other, and then you take a second wire with its coating, and that's how you would actually wire your house. And unfortunately, since we're not in class together, we would actually wire a light bulb, an outlet, and a light switch. We would actually do all of that together in class had we the opportunity, and unfortunately we don't have that opportunity. Now, let's take a look at this. I've got V equals I times R. So if I have 12 volts coming from my battery, and I've got 6 ohms here, V equals IR tells me that I get 2 amps going through this branch. And then I get 2 amps going down this branch because I get a drop of 12 volts and then a drop of 12 volts. Every loop has to use up 12 volts. I get 12 and this branch uses 12. And then I get 12. This branch has to use and this branch has to use. So what we're seeing here is that in parallel, every time you add a new branch, you have to add another set of current. So I get 2 amps, and then I get 2 amps, then I get 2 amps. So in this picture, how many amps are coming out of the battery? 2 plus 2 plus 2 plus 2, 8. And when you have high current, current is what damages humans, it's what damages electrical devices. Everyone's like, oh, high voltage. Voltage doesn't do anything, it's the current. 2 amps, no big deal. But maybe 8 amps is too much. Well, this segment of wire here is getting 8 amps. So is this one. So is this one. So is this one. So our 8 amps could be dangerous. Wires could melt, they could heat up, could cause a fire, or it could just break and then I have to figure out where it broke and then I have to pay to get it all fixed up and then got to rip the walls out of my house. So what do? Right here, D, device. We put in the designated weak spot. We call this a fuse or a circuit breaker. You have these in your house. And what happens is the more branches you have in parallel, the more current is coming to that particular part of the house. And if too much comes, your circuit breaker trips. So this happens quite often in bathrooms and kitchens because you have lots of outlets and lots of devices. So let's think about the bathroom. You've got a lot of lights. Maybe you've got a heat lamp. Maybe you're charging your phone. Maybe you're playing a stereo speaker. Maybe you've got a hair dryer plugged in, an electric toothbrush, electric toothbrush plugged in. Think about all the things you might have. And all of a sudden, all the lights go out. Like, oh, power outage, but then you realize the rest of the house still has light. That's because you have just tripped the circuit breaker, the designated weak spot. So we have a spot that is designed to fail before any of the wires get too hot and fail. And when that fails, I can fix that. So I have an example of a fuse and a circuit breaker. A circuit breaker is just a heavy-duty light switch that flips off when it gets too hot. A fuse is a piece of metal that will literally melt when it gets too hot. In looking at Google images of a fuse, this is what they commonly look like. So this right here is a straight fuse. There's a piece of metal. It's encased in glass. And what happens if it gets too hot? That metal melts. Right here, metal connected by this little piece right here. What happens if it gets too hot? It melts. And what does it look like? Right there. There's a fuse that has a blown fuse. Now that little piece of metal melting, not a big deal because this right here is extremely inexpensive. I buy a pack and I can replace it very, very easily. The downside is it's just a pain in the butt, and if I don't have one on hand, I'm out of luck. A Google search for circuit breakers shows a heavy-duty light switch right there. This orange heavy-duty light switch, a heavy-duty light switch. It's a light switch that basically gets turned off when it gets too hot, and all I have to do is flip it back. Now, could I flip it back and then it goes out again? Yeah, if you keep on using too much current, it'll just keep on failing you. The nice thing is that I don't have to replace anything. I just flip a switch. They're bigger and more expensive, and I have to actually wire them in, but they are reusable again and again and again. Here we are down in the basement of the Lohr household amongst all the Halloween bins and old photos. And this right here is my circuit breaker. And so what you'll notice here is all these black switches that look like light switches. They're extra hard to move back and forth compared to a normal light switch. But what's going to happen is that if I have too much current going into a particular part of the house, those wires could overheat and malfunction. So once we reach a level that is deemed unsafe, these are designed to switch off. So this is the designated weak point. If we're going to have failure, it's going to happen here instead of happening in the walls of my house. All I have to do is come down here, and if something were off, so right here, and most people like to label these the laundry light. So if something happened in the laundry room and this boom happened, all I have to do is go and push it back on.
and just like that. And so if you're doing this correctly, you're going to have each one of these for a particular bank in your house. So bedroom number 1, bathroom number 1, master bedroom, whatever, all the way through. Now, do people wire this by themselves without professionals? Of course. And do they sometimes have weird things all kind of brought together in one circuit breaker? Yes. I can tell you I've got some weird ones where I've got a downstairs light and an upstairs outlet all wired together on one. So all depends on who is doing the wiring initially. You've got some big ones on here. The range, that is your oven. You've got down here we've got the dryer. The dryer draws a lot of energy. So you got a double here and you got a double here. Some of them require a lot of juice. So that right there is your circuit breaker. The nice thing about a circuit breaker is that they are reusable. It goes to off, you switch it back to on, and just like that, you're ready to go. As opposed to a fuse. With a fuse, it burns out and you have to replace it. It's not very expensive, but it is inconvenient. Now your circuit breaker is rather large, which isn't a big deal when it's for your house. But when you are looking at cars or boats, having a bunch of circuit breakers is going to be a bit of a challenge. So what we're going to do is we are going to pop the top here and take a look at the fuse box inside my minivan. So we got this. Let's see. So this, trying to do this one-handed makes it a bit of a challenge. So this goes right here, and so right over here we have our fuse box. And so what you'll see in here are all these fuses. I've got 30s, I've got 25s, 20s, 10s, 15s. These are all the fuses that are running all the interior things in my car, lights and everything else. So if there's any problem, these are going to blow. And what I have inside is I have a list of all of the different types of fuses and their locations and their names, their numbers. So that can be pretty complex in terms of what you're able to find there. When I look at my user manual for my awesome minivan, there's a spot for my fuses, and what you'll notice in here is you will notice the different markings, the F21, F22, F23 that we saw under the hood, and then you have your 10 amp, your 25 amp, so all the information. So obviously you have your list here showing exactly where we just looked under the hood. So it's a bit of a process to replace your fuses, but certainly not impossible. Something you could definitely do all on your own, maybe with a little help from not this YouTube video, but from YouTube or whatever else. So that's a fuse, which is different from your circuit breaker, although they perform the same function. The designated weak point. My circuit breaker, I just switch it back on. For my fuse, I have to own, possess, and replace the fuse. They are not expensive, they're just a hassle.
So continuing on, another class activity that we would have done, so the variables that we have, potential, current, power, resistance, we'll talk about power here in just a second, and then resistance, so we have that. All right, so current kills, that's the phrase, current kills. It kills electrical devices, it kills human beings. So we have V equals IR. You never see a sign that says danger high current, because current varies. Current depends on these other two variables. So if I have a sign that says danger high voltage, that doesn't necessarily mean it's going to cause me harm. It'll give me harm if I don't have enough resistance. So think about humans. If we want low current, I want big R, because I times R equals V. Voltage is a value that my power lines have. So I times R. If I want this product to equal V, but I don't want I to be too high, I need R to be big. Lucky for us, dry skin produces a decently high resistance. It's why you can touch ends of a battery and not get electrocuted. Now, as soon as you have wet skin, that lowers your resistance. It's why if you watch a movie where they have a torture scene with a car battery, they've got wet sponges. It's why if you have wet fingers and you touch a battery, you can get zapped. I can honestly say I've never done this, but I know of people that will take a 9-volt battery and touch it to their tongue and they'll get a little bit of a zap or something. I don't know. Seems crazy to me, but I'll pass. So wet skin lowers our resistance. Now, everyone's always afraid of wet skin and electricity, and that's definitely something you want to be concerned with. But if the electricity in your house is functioning properly, then you don't have to worry about wet skin because all the electricity is housed in the wires. But if there's a malfunction, wet skin will definitely cause a problem. So anytime you've seen in the movies where they have some kind of water involved in electrocution, that's definitely something that we want to concern ourselves with. So the sign always says danger high voltage because we know that the voltage is high. If I have equally high resistance though, then the current will be safe. That's why they might use really big, thick rubber gloves and be safe. So here's worksheet number 2 showing a series as well as a parallel. You can go through that if you'd like to get some additional insight. Now when it comes to brightness, the more energy my particles have, the brighter it's going to be. The more current I have, the more charges going by, the more I have to see. V and I together give us our brightness. If I scroll down, volts is a joule per coulomb, and amp is a coulomb per second. Joules per second is a watt. That's power. We learned power at the beginning of the second semester. So we have an equation. P equals V times I. The more voltage and the more current gives you more power. Think about when you buy a light bulb. If you were to buy a light bulb, the light bulb is going to have a power rating, a 60-watt bulb or a 100-watt bulb. The new bulbs have a very, very low wattage, but they give you just as much brightness. Even the new bulbs that might only be 8 watts will still have on the side stamped a 40-watt equivalency or a 60-watt equivalency, etc. Now, if we remind ourselves what power is energy divided by time. So energy divided by time, if I rearrange that, energy equals power times time. When you buy electricity from DTE, you're not buying power, even though you might call it the power company. You are buying energy, literally energy. Now, this is a watt, joules per second. This is a second, so I can get a joule. Here's the problem. A joule is a teeny tiny little value. It'd be like telling someone, hey, I'm driving to Florida, how far is it? Well, it's this many centimeters. Well, that doesn't make any sense. You're not going to use centimeters. That's way too small. Same thing for electricity. So what do we use? Instead of watts, we use kilowatts. Instead of seconds, we use hours. And we call a kilowatt times an hour, we call it a kWh, a kilowatt hour. How many kilowatt hours of energy have you used? That's the phrase that we use. So if you were to get your bill from DTE, you are going to get a bill that says you used this many kilowatt hours, and then they simply apply the rate to your number of kilowatt hours. So maybe it's 10 cents per kilowatt hour, maybe it's 20 cents per kilowatt hour. They do simple math and they send you a bill. Now, your power, your electricity, either comes through lines that are in the air, or those lines at some point go underground and they connect to your house. In your house or outside your house, you got some kind of an electrical box. A Google search of the electrical box looks like these cylindrical glass encased things that you will see outside your house. Every house has them. Maybe they're not cylindrical anymore. This one right here is a classic. You can see that it's got these little dials. That one spins around super fast. When that one goes around once, this one clicks over 1. When this one goes around once, this one clicks over 1, just like the odometer of your car. And this tells us how much energy, kilowatt hours, is going into your house. People from DTE or Consumer Energy literally walk to your house, read your meter, write down the number that's on the side, and they leave. It's becoming more and more digital, so you don't have as many people literally walking to your house, but that's called the meter reader. And they literally go to your house, they read the meter, they record it, and they figure out how much you use each month. So they don't do power times time or anything. They just have a meter that does everything for you.
All right, here we are outside the lower house. If I go to the side here, here we go. We've got a round little box. It looks digital instead of analog. Level 5, not sure what that means, but I see kilowatt hours, 31914 kilowatt hours. And if we keep on watching here, which we're not going to do, we're going to see that number slowly tick up. And when my meter reader comes out, they're going to read this number. They're going to compare it with the last number. So this right here is for my DTE energy. So that is for the amount of electric energy that is going into my house. A kilowatt hour, that's power times time, gives us energy. Now at another location on the lower house, we have something that looks similar here. So there are those analog little dials that are going to spin around. This right here is consumer's energy. This right here is my gas meter. So it looks very similar. And so you can see one of these little black dials going around, and a 1/2 foot and 2 feet, and I'm not even sure what any of this means. I'm not much on my gas, but same idea. So whatever's flowing into my house, these spin around and tell me how much has gone through since the last time. So I can see thousands, 10,000s, 100,000s, and millions. So here we have my DTE electric bill. So address, account number, your bill, all that kind of stuff that most people are interested in. But if you get down a little bit further, you have some options. One option is always to compare your bill. So I can compare month to month. So I can see that this month compared to last month has gone up a little bit. I can compare year to year. Year to year, you'll notice there's a huge change. Any idea why this year during the April month it's so much higher than last year? And of course the answer for that would be because of COVID. We're stuck home 24 hours a day using TV and lights and things like that. So that makes perfect sense when I look at that. But what I really want to look at here is my billing statement. So looking at my billing statement, as I go down, it gives me how much I paid last time. I can see my my yearly usage here. Not sure why July and August is so high, because we don't have air conditioning. Might be something I should probably look into. But continuing down, here is our page. And so what you'll notice is that I have over on the right hand side here, you'll notice that I have my pay period, my days billed 31, and the meter reading. So the actual number read on my meter. And I showed you outside what my reading was. It was, what was it, 31914 or 329, whatever it happened to be. Well, here we can see those numbers actually match up. I use 382 kilowatt hours, kWh. So I slide over here, and what do I have? I've got the rates. My power supply capacity charge is $0.037050. So 3.705 cents per kilowatt hour. So they've really go with the sig figs on this one. The non-capacity charge, 0.0468. The cost recovery, 0.0015. Yes, they are charging me 0.15 cents per kilowatt hour for a grand total of 60 cents. Slide on down, delivery charges. Delivery, so I'm assuming I'm paying for the wiring and whatnot. Service charge, just a flat fee. Energy waste reduction, 0.5 cent. How about the nuclear surcharge? 0.0008. So yes, you are reading that correctly. 8/100ths of a penny cost me 32 cents. And of course, residential Michigan sales tax, $2.63 on my electricity. Every single bill will have all of that for every single resident. So you've got your meter reading that's done over here, and then you've got the charges over there, showing you how I got a bill of $69.32. So that is your electric bill from DTE. So your gas bill, your water bill, all of it will look something similar, giving you a usage and giving you the rate.
Last, to solve problems, what is your resistance? Remember, your resistance is measured in ohms. If I have multiple resistors in a series, just add them up. I can figure out how much voltage my battery has, that's given to me. I can figure out how much resistance my battery encounters, and then I can figure out the current coming out of my battery, and then I can figure out the individual pieces. Right now we're only doing series, and so that's all we'll worry about currently. I can also figure out any power ratings. That'll tell me how bright my devices are going to be if I'm working with light bulbs. And then here are some examples of series and parallel work. You can use those. Again, this is all posted, so there are some samples. We will start with series this week. We'll get to parallel next week. And that's it. So make sure you go through that, and that'll help you with everything we'll be continuing with for the rest of the week. Now at the end of this section of notes, down at page 46, these are things, again, we would have been doing in class. These are very useful things for you as an eventual homeowner. A short circuit is where you basically have a path around the resistance. Your current is going to flow the easiest path. So if I have a path that offers no resistance, all my charge is going to go that way. Resistance over here, nothing's going to use this route. So I'm going to go with this malfunctioning, and I'm going to have no resistance. Think about this: no resistance, huge current, and that can be dangerous, which is why we have our fuses and why we have our circuit breakers, so that we don't get wires that are overheated. The next one here talks about how the holes in your wall, which is going to be very important to you, how it differs slightly from what we're using in class in our examples with batteries. A battery has a positive and a negative. You don't have that for the holes in your wall. What you do kind of have is a hot wire, that's the high potential, kind of like a positive. It's not positive, but it works kind of the same. The neutral is our low potential. This is going to be a black wire. It's going to have gold or brass screws. This one is going to have a wire with a white coating, and it's going to use the silver screws. That's just the standard for how we can remind ourselves which wire should be connected to which screws. Should I have the hot or the neutral? The screw color actually tells you. Devices that have a hot, they purposely make the hot harder to reach, because if you touch the hot, wet or dry hand, you're going to get zapped. Touching the neutral, nothing happens. The ground wire is just to make sure any electricity that ends up where it shouldn't doesn't go into you. So that's that third wire, and usually it doesn't have any coating at all. Basically anything that has a metal structure to it will commonly have a ground wire, especially things that have a lot of electricity that go through them, things like a microwave oven perhaps. Your switch. If I take a look at this picture here, my switch is a simple way of turning off the power. So a convenient break in the wire. Well, if this is my power supply coming from the bottom of my house, if I cut the hot wire, this entire section and the bulb itself is now neutral. It's low potential. It's safe for us. Now, is it possible for me to come along and put the switch in the wrong spot, since I'm going to wire my own house? Because I know YouTube, and I put it right there. Could I do that? Absolutely. But if I did that while leaving this connected, if I put the switch in the wrong spot, what happens when I turn off my electricity, when I flip the switch? Hey, the light went out. Yep, because I broke the path. But this whole wire is all charged up. So that means if I turned off my light and then undid the bulb, I could zap myself if I got too close to that socket. So you always want to make sure you put your switch as close to the hot source as possible. So on the hot side of my light bulb or my device, that's where my switch should go for safety. So if we Scroll down here. I guess I should have looked down before I did my erasing. This right here is going to be bad because this whole thing is loaded up with high potential, ready to zap somebody. When you touch the wrong thing with your hand, you are a path from high potential to the ground, low potential. You don't want to be that path. Being that path is bad because if you're that path, electricity is flowing through you. You are getting electrocuted.
Now when it comes to our light switch is just a controlled break in the circuit. So it's where we stop the flow. Now we can stop the flow anywhere we want. The question would be, where would the smartest place be to stop the flow? Well, if I have a hot wire coming in, anything that hot wire touches is going to be hot. It's going to be electrified. So if I'm going to turn off my electricity, I'm going to find it's probably the smartest to do this on the hot side. If I cut the hot side, that means the entire rest of the circuit is now touching the neutral, and it's going to stay at low potential. If I put the light switch on the neutral wire instead of the hot wire, it'll still turn off my light switch. The only problem is that now, when I turn it off, all the wires in that circuit are still hot. They just don't have a way to continue on to the neutral. So you always want to make sure you put your switch on the hot side. So if we take a look in here, oh, a little dusty. If we take a look in here, I've got two brass fittings. We've talked about how brass should be connected with the hot as a reminder to the people using it, which is why I have brass screws here instead of the silver screws that I had on my outlet previously. And so what I see is I can see my wires in there, and I can see that there's black wires coming into the back side of here. Again, it's hard to see and I don't want to take this all apart. So our switch is always put on the hot end. Now, could someone wire their switch on their own, not realizing that black was hot and that's where it should go? Absolutely. Definitely a possibility.
So this right here is a picture of what we would have done. We would have wired in an outlet. We would have wired in a light switch. So if you take a look, I've got black wire as my hot. I've got red wire as the neutral. The green wire is the ground. And what I have is I've got my wire coming through. We cut the end off, pull out the black from the red, and we connect. I take a second wire, cut the end off, black and red, connect. So I have black going to this side of my outlet and then black continuing on. I got my light bulb way up here. I want to put in a light switch for the light bulb. So I cut the wire, I take out the black, I take out the red. I just put the red together, just twist them together, and I put my light switch on the black. If you're ever looking to do something like this, make sure you double and triple and quadruple check that you know what you're doing. Here's the outlet in your wall. You got the skinny side, you got the long side, and you've got the ground. So the skinny side is hard to get to, which is why that is going to be the hot, and this is the easier one to get to. That's going to be the neutral. If you have an old plug or you got an old outlet, you might not see a difference in the sizes. Scrolling on down here, this is a light bulb socket. The threads are metallic, and then down here is the other end. So notice that is the brass color, and this is the silvery color. So this should be the hot wire, and this should be the neutral wire.
Now, if we remove our Spider-Man nightlight and we take a look at our outlet here, you recognize these hopefully from every day of your life. You've got two slits here that you have where your energy comes out, and you've got this third one. So this third one here is going to be our ground. This is our safety mechanism that removes any electricity that shouldn't be somewhere. It goes through here. These two slits are how we get our energy. Now, we've talked about high potential, low potential, positives and negatives. The outlet that gives us the electricity we get from DT works just a little bit differently, but we can still kind of think of it as high and low. So this right here is called the hot. This is the high potential. This is where the energy comes in. This right here is our neutral. It's kind of like our negatives, where the energy goes back out. If this thing is designed properly and wired properly, the hardest part to get into is going to be the most dangerous part. So that's why the smaller slit here is going to be our hot, and that's going to be the neutral. So that means what I could do is I could take a paper clip, I could take my pencil here, and I should be able to stick this right into the neutral with no fear of getting zapped, because this is the low energy side. All the energy is coming out of this. Now, should I do that? Probably not, because there's plenty of people that are now experts because they watch 2 things on YouTube when they wire up their own house. Is it possible that they put the wrong wire with the wrong side? Absolutely. Last thing I want to do is stick my finger into the neutral and find out that someone wired it incorrectly and get zapped. Now, if I unplug that as well, what I can do is take off this plate and get a look at what the insides of our outlet look like. Now, sometimes when you put the plate on, sometimes it kind of sticks to the paint that's already there. You gotta pry it off a little bit. All right, and now what we have here is our outlet. So you'll see that it's screwed into the wall here, so it's nice and solid still. But if we take a look nice and close, now if we take a look in there, you'll see the metal right there. You'll notice it's kind of a brass color. And I look on this side, and I see more of a silver color. That's more coating. So silver should be your neutral, and gold should be, or brass should be, your hot. Now, doesn't mean that it was wired properly, but that's why you'll see silver on this side, and you'll see the brass color on this side. So the brass would be where my black hot wire would be connected, and the silver is where my white neutral wire would be connected. And by black and white, I simply mean the coating on the outside of the wire, the insulation. It's all copper wiring. And again, that third one here, that's just my ground. So again, I could stick something in there and be safe, because that's just going to the ground. And the ground quite literally is a metal stake pounded in, a big metal stake pounded into the ground near your home. And that's where your ground goes, and it's also where your neutral actually goes. It just goes into the ground. So we got our energy coming in, and it goes out through the neutral. So here we have is a floor lamp, and I've got my light bulb inside. If I unscrew the light bulb, a little bit stuck there. If I unscrew the light bulb, what I'm going to see inside is metal threads. And if we wanted to get a closer view here, let's do exactly that. So what we have are metal threads. So you'll see the metal threads along the edge right there. That metal is going to touch the metal of my light bulb. So my light bulb has metal along the edges. So that metal connects with the metal threads. And what color do those metal threads appear to be? They look awfully silvery and white to me. Now, in looking at my light bulb to complete the circuit, I need to connect to the end. So the end, that's where my hot is going to come in, and it's going to come out through the wires. So if I glance up here and I look at the very end in there, what do I see? I see a brass / coppery looking tab right there at the end. I don't want to touch it because I might get zapped there, but right there at the end, there it is. It's brass, reminding me that should be the hot. This should be the neutral. Why is the hot way far down there? Because we, as a society, try to make the hot part the hardest thing to touch. It's going to be harder to reach all the way in there and touch that brass piece than it is to touch the sides where the threads are, which is why we have our hot way down in there. And again, it can always be connected incorrectly, so never just assume. Now, if someone were to, this is turned off, so I could touch anything I wanted because if if it's wired correctly, I have cut the power source at the hot. But if I were to turn this on and reach my finger in there, I could definitely get zapped. So that's why I want to make sure we don't stick our fingers into any sockets, whether it's an outlet or whether it's a light socket.
All right, so we talked about short circuits and how to wire devices. Some of these other diagrams here, this is how if you have a light in your house that can be turned off and on with 3 different light switches, that's how it connects. If you have one that has 2 light switches, like a long hallway, that's how it connects. So we have a way to kind of draw those. So if you're interested, I love playing with circuits and playing with the wires and piecing everything together. It is a lot of fun. That's how you would wire in your 2-way switch. Sometimes it's called a 2-way switch, sometimes it's called a 3-way switch. That's how you would wire those in. So again, it's a lot of fun, and we would have spent a lot of time doing that in class. So that's it.